Today we are going to talk about, I'm going to move the microphone over a little bit. I should have brought my microphone, but I didn't. So I'm going to use the computer's microphone. I'm sorry about that. Okay, so we're going to talk about parallel circuits today. And a parallel circuit is one that has more than one path. What's going on here? Okay. Series circuits have only one path. Parallel circuits have multiple paths, more than one. And take a look at the black line circuit, the red line circuit, and the blue line circuit. They're actually individual branches of one single circuit, right? This is one total circuit. It's got one battery supplying the whole circuit. So these are parallel branches. Okay. I want you to take a look at these paths, though. Black path, red path, blue path. And when we read current, if you read current, notice that really and truly they're suggesting that each one of these resistors is drawing 1 amp. So notice that this is actually in a series portion of the circuit. Each one of these is reading the current that's going out. At this point right here, notice the red, the blue, and the black, that it's reading all three of the resistors' currents. So it's saying 3 amps. Over here, it's in series again, so it's all the current that goes out to these other two resistors has to go through this meter. Okay, good reminder that series circuits, that ammeters have got to be turned into a series circuit. So here we have a visualization that each one of these points are actually series points in this parallel circuit. So even though a parallel circuit is, everything is parallel, it's got multiple paths, it's got points of that circuit that might be, if all the currents are going through that one point, then that's a series point in that circuit. Okay? Notice the area before, right after the battery, the current's going out, all the current's going through that point, all the current's having to go through that point. When it comes back, it all has to come back through one point. So those are the two series points in this circuit. Okay. Also notice, like I said, if you're reading the current that's going past meter number 2, it says 2 amps. It's reading the red and the blue both. It's not reading the black because the black path, the black current path, the black branch does not go through that area. Okay, ammeters must be connected in series. So to indicate the current in one branch, in this case one resistor, must be connected in series with only one resistor. Now the reason I've done this is because students in the second semester have trouble with this idea. So I want to get this clear now. Notice meter number 2. And notice that it's only in series with resistor number 1. You see it? Can everybody see that clearly? And how about ammeter number 4? It's in series only with resistor number 2. And then the 6th ammeter is obviously only in series with resistor 3. Everybody see that? So they would all be reading, if this thing as it was before, it would be reading 1 amp on 2, 4, and 6, right? And on 1, it would still be reading 3. On 3, it would be reading 2. And on 5, or is that backwards? No, yeah, 5 would be reading 1, right? Okay. Small portions of the parallel circuit are in series. This is a parallel circuit. The black path is branch of the circuit parallel with red, parallel with blue. And that's pretty typical of AC home setups in that all the loads are in parallel. Why? Because we want the same voltage going to everything. And what is true in series circuits, in parallel circuits, voltage is constant. So our voltage supplied from this panel, if it's a 120 volt circuit and it's going out to a receptacle, a light, a receptacle, a light, a receptacle, a light, if they're all turned on, they're going to get 120 volts each, right? And that's the idea. That's what you see at all the receptacles and the lights in a house. And that's why everything's hooked up in parallel, so they get the same voltage. Okay. Now, something a lot of people have trouble with is seeing the voltage differentials or the voltage potential difference. And I want you to notice at any point along the red line, anywhere, pick any place at all, and read down to the gray line, and what will you expect to read? 120 volts, right? Because that's the potential difference between line A and the neutral or grounded conductor. But what about if I choose the point A at this receptacle and the point A at this light when it's turned on? What is the potential difference between the hot over here and the hot over here? None. Zero. That's exactly correct. There's no potential difference. Now, we've talked about this before, and when you come out of this load, what potential do you have? Zero. That's correct. Okay, so what is our potential difference if we pick a place on the gray line, if we go from this point to, let's say, where the gray wire is coming out? What potential difference would we see? Zero. Very good. Okay, now, would we expect to see 0 volts on the neutral conductor? Not necessarily, because to ground, it might have a slight potential difference. Hopefully not too much in a 124 center grounded system, Edison 3-wire system, but there might be some voltage on it. If you have a light turned on, is there current flowing on the neutral conductor? Right on. That's correct. So if we have something plugged into this receptacle and we have this light on, something plugged into this receptacle and this light on, something plugged into this receptacle and this light on, is there 0 potential on the neutral conductor? No. It might be at 120 volts. Okay? It'll be less because theoretically it's 0 volts. Theoretically. But it's got current flow, right? And if you get in the path where you're a shorter circuit down to the earth than, or back to the transformer, back to the generator, then the wires going back, you might become a ground fault circuit. Don't become a ground fault circuit. That might not be good for you because the breaker never ever kicks off on a ground fault because you're a high enough amp resistance load that the current through you is only going to be 4 or 5 amps maybe, but it's still not going to kick off ever, right? 4 or 5 amps on a 15 amp breaker never kicks off. How much does it take to kill you? Less than 1. So that's 4 or 5 times what it takes, or a lot more than that, to kill you. And you might be getting that from a neutral conductor. So be careful even with the neutrals. Okay. The voltage drop across all these loads is the same. In other words, the voltage supplied to everything. Voltage drops in parallel equals the supplied voltage. Whatever supplied, in other words, voltage is constant. That's one of our rules. Okay, current is one of our rules. Current is additive. That's our other rule. The total current is equal to the sum of the branch circuits. So, pardon me. Thank you. So the current total is the only thing in parallel that's additive. Remember that. Current is additive. Okay? In parallel, current is additive. So the current through resistor 1 plus the current through resistor 2 plus the current through resistor 3 plus the current through resistor 4 will be the total current. Okay, so let's look at what would happen if we have that situation. If resistor 1 is flowing 2 amps, resistor 2 is flowing 3 amps, Sorry about that being off the page. Okay. And resistor 3 is flowing 5 amps. What is the total current flow? Total current flow. Well, 2 plus 3 plus, 3, I put, 5. Okay. So 8, 9, 10 amps? No, you have 3 amps here, we have 5 amps here, and we have 2 amps here. 10 amps. Okay, if resistor 1 is flowing 2 amps, resistor 2 is flowing 3 amps, and resistor 3 is flowing 5 amps, what is the total current flow? 10 amps. Where will this current be indicated? 10 amps. Where will that be indicated? Right here. Resistor, ammeter number 1. If we look at ammeter number 3, this one right here, you see that it's in series with part of the circuit, right? Everything to the right of it, it's in series with. Is that correct? So what would it indicate? 8 amps. Because it's got the flow of both R2 and R3 going through it. Okay, and as I said, the reason I wanted to make sure that this is in this slide is because in the second semester, there is a lab project where you need to realize this, and a lot of people forget. So it'll be there so they can see it again. The first and easiest rule to use for parallel resistance is that if you have equal resistance resistors, then you can divide that resistance by the number of them. Okay, so R is equal to, RT is equal to R divided by the number. So RT is equal to R over the N, the number of them. Now, that's rule number 1. So let's say we have 5 resistors that have 25 ohms apiece, 2,500 ohms apiece. How much would my total resistance be? 2,500 divided by 5. 500 ohms, okay. Second and very easy rule to use is, oh dear, it screwed up my symbols again. Okay. For parallel resistance is known as the product over the sum, but it only works on 2 resistors, R1 and R2. Wow, I can't believe how messed up it screwed up my symbols. Okay, this rule can be used on more than 2 resistors, but only if you start grouping them as equivalent resistors. But that's a good idea to start working on because you need to do that in the future. Okay, I think I have an example of that. Oh, no. Wow, it dropped all my math equations completely out. And these are word math equations. Okay. So what this was supposed to say, let me go back and cover that real quick. What this is supposed to say is R1 times R2 divided by R1 plus R2 is resistance total. And it just dropped my math formula completely out. Cool. Okay, now this one is the most difficult to use, but this is where your TI-30X2S really shines. This is called the reciprocal rule. And we're going to come back to that and do some practice on it. But that formula does not say 1 is equal to all that. It says 1 over resistance total is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over Rn, meaning however many we happen to have. And we can just keep going. And here is what your 3x5 card is going to look like on the back from now on. After today, the back of your 3x5 card will have this. Now I want you to notice that we have a blank area right in here for a reason. So, because another rule is going to go in there. On the front side of our series card, we're going to have another rule that I didn't realize that I've forgotten to give you, but we'll do that later. And we'll go back and pick up what's called the general voltage divider rule. Okay, so we have PIE just like on the front side, EIR just not like on the front side. 1, the most important rule, voltage is constant. 2, current's additive, and resistance, the three rules for resistance, and the most easy one to use if you're using the TI-30X2S is the reciprocal formula. 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus on and on and on. Now, recall that I said save a little space in the lower left-hand corner 3x5 card on the front and the back. And the reason for that is because we're going to have the current divider rule. Oh, maybe it was right there. Maybe it used to be right there where this question mark is. God darn this thing. Okay, the current through any resistor is the total current times the total resistance divided by the resistance of that resistor. Does that make any sense at all? Okay, good. But what it would say is R sub X, write this down, R sub X is equal to RT over RX, in other words, that particular resistor, times total current. So it's a proportion, It gives you the proportion of the resistance, which is directly related or inversely related to the current. So we're going to have it on our 3x5 card. Let's go back to that. Oh, it's not there yet. Is it on here? No. Okay. We're going to stop. Oh, darn it.